here's a extra example from 7.3 dealing with sample means. So this situation at the Nutty Peanut Company, peanuts are placed in jars by a machine. The distribution of weights in the jars is approximately normal. Okay, I should say normal there. Let's put it. So the mean of 16.1 and standard deviation of 0.15. Okay, so we kind of know basically, if we want to think about this before we get going, normal distribution, these are the weights, average of 16.1 for each jar. Okay, so question A here, without doing any calculations, explain which outcome is more likely. So would it be more likely to randomly select a single jar and finding the weight is less than 16 ounces, or randomly selecting 10 jars and finding that their average weight, okay, there's a sample mean, is less than 16 ounces? Okay, so this one again, they want you to kind of be able to explain it without doing any calculations. So the issue here is that it is more likely to vary. There's more variability in a single jar than there would be in 10 jars. Okay, if you remember the formula, I know we're not using them, but as your sample size gets larger, you have less variability. So what that means is if you had a sample of 10 jars, they are going to be closer, or the average is going to be closer to the mean than just an individual jar. So in this case, it's more likely for a single jar to be a little bit farther away from the mean. That probability for a single jar being less than 16 is more likely to occur out of one single jar than if you were to average 10 jars. It's kind of like thinking like safety in numbers almost. As the sample size gets larger, you should be closer and closer to the mean and have less variability. Okay, so our answer to that one, again, it's more likely that a single jar will weigh less than 16 ounces than it would be for a sample of 10, okay? Because the sample mean, as the samples get larger, will get closer to the 16.1. Okay, now let's actually do some work here. There is a part B. Find the probability of each event. Okay, so let's do the probability that a single jar is less than 16 ounces. Okay, so this one is just a straight up normal CDF problem like we did back in, I think it was chapter 2, because again they told us the population's normal. So we're just going to go ahead and do a norm CDF. Okay, it was just like the picture I drew before. Up here, less than 16 ounces, so everything of a left bound of negative 9999. Up through 16 ounces, they're telling you the mean is 16.1 ounces. They told you the standard deviation was 0.15 ounces. Okay, so that will give us the answer. This is just like a problem we did, again, like I said, back in chapter 2. So let's find that. I thought I had my calculator open here. Okay, so let's do the calculation here. Again, it's a normal distribution, so second distribution, normal CDF. And we said it's from negative 9999, just give it some lower bound, all the way up through 16. And then mean and standard deviation were given to us of 16.1 and 0.15. Okay, so that's going to be your probability of getting any individual jar being less than 16 ounces, so about 25%. Okay, part B, or the second part of this is now, what about having the mean of 10 jars be less than 16 ounces? So the only thing that changes here, so we're trying to find the probability that a sample mean is less than 16. This top one, you could think of it as like just what's the chance that any individual value is less than 16 ounces. The second question dealt with the sample of size 10. What are the chances that that is less than 16? Okay, so the only thing that's going to change here is the standard deviation. Okay, we have a formula that says for sample means, if we remember for the sampling distribution, we know the mean of the sample means is still the mean. we know the standard deviation of the sample means is the standard deviation given to us, but we have to divide by root n. Okay, that's why as n gets larger, the standard deviation gets smaller because the n is in the denominator here. So bigger denominators make the entire answer get smaller. So our setup is going to be exactly the same as what we did before. We know it's normal CDF, okay, because again the population was given to us as normal, so the sample distribution is going to be normal. Same setup, it's still from negative 9999 up to 16. It's not a negative there. The mean is still 16.1. Okay, it's the same mean as before. Now the standard deviation, we just need to take the 0.15 and divide it by the square root of our sample size, which is 10. Okay, and that's just going to be the only difference. Okay, the only difference is that and that. Okay, so whatever the sample size is gets divided by. We divide by the square root of it, I should say. So let's calculate that real quick. Okay, so it looks like we're going to do, again, it's a second distribution. I'm just going to retype the whole thing here. From negative 9999 up through 16. The mean, again, is still 16.1. And we're just going to take our original standard deviation divided by the square root of the sample size. Okay, so that goes in there as the last thing, and that's going to give us an answer of only about 0.017. So it's a much smaller percentage than we got, okay, because this was the single jar being less than 16 ounces. The chance that the average of 10 of them, much less likely because, again, there's a lot less variation. So everything's going to be closer to the sample mean. Okay, so that kind of verified our answer for part A. And we can see the process is very much the same, just make sure we watch the standard deviation. Oops, that's the wrong thing. We don't want to see that.